Hello students, in continuation with our discussion of Paper-2 syllabus, we are with a second chapter, Logic Gates and Boolean Algebra. In this session, you will learn the sub-content of this chapter, XOR Gate and its applications, in which you will learn the concept of construction of XOR Gate by using basic logic gates. Secondly, we will try to familiar with very basic applications of XOR gates. First one as a 3-bit parity checker, and second one will be as controlled inverter along with its use as well. Let us start with the very first content of today's session, that is 2-input XOR gate and its construction. You have already learned about different types of logic gate including XOR gate. Let's see now here a brief review of 2-input XOR gate. We can represent by using a symbol A and B as an input and Y is the corresponding output, right? Boolean equation for this 2-input XOR gate is what? Y is equals to A exclusive or B. Y is equals to A exclusive or B. In short, you may read it as A XOR B. In the form of simplified equation, the equation becomes as equals to A and B bar, dot means and, or A bar and B. Now, this is the logic performed by the 2-input XOR gate having the input as A and B. So we can implement this logic with the help of basic logic gates. That means we can obtain the construction of a logical diagram for this equation Y equals to A and B bar or A bar and B. Let's see here the way of construction by using basic gates. A very simple diagram. To get the first term A and B bar, you have to use an AND gate. Having A as input, second input as a B with inversion B bar. So ANDing of this will be as A and B bar. Then second term of the equation is A bar and B. To get the A bar from A, use a NOT gate, you'll get the A bar. Then apply second input B to the second AND gate here, whose output can be as A bar and B. Now, these two outputs of AND gate given to the input of one more basic logic gate, 2-input OR gate, whose output Y will be equals to, as per equation, A and B bar or A bar and B. So we will get required equation by using 2 number of NOT gate, 2 input, 2 number of OR gate, 2 input, 1 OR gate. I'll repeat it. We required for construction of XOR gate with the 2 input, number of basic gates, 2 numbers of NOT gate, 2 input, 2 numbers of AND gates, and 2 input, 1 basic OR gate, with which we can get construction of XOR gate. And truth table of this is already known to you. A and B as an input, Y is the output. Output we can define with the XOR combination. That means exclusion of only last combination in the basic OR gate, where in basic OR gate for 1 1 output is to be 1. It is here in XOR, it is 0. I'll read the content of truth table once again. Here A and B as an input and Y is the output. So 0 XOR 0, not OR. 0 XOR 0 will be equals to 0. 0 XOR 1 as well as 1 XOR 0 equals to 1. But 1 XOR 1 will give 0. This truth table is useful in our next slide, where we have to go for the more than 2 input, an example of 3 input as well as 4 input XOR gate. Idea of construction remains same. That means 0 XOR 0 is 0, 1 XOR 1 also 0, but 0 XOR 1 or 1 XOR 0 will be equals to 1. That is by this logical equation. I'll go one by one. First application of the XOR gate as parity checker. Before that, let me have an idea. What do you mean by the parity of binary bits or parity of data? As you know, in case of digital electronics, bunch or the groups of binary bits are being sent from one device to other device, or the group of binary bit are being stored in the memory devices that contain so-called as group of binary bit is also known as a data. Now, in the field of electronic communication, to verify whether data transmitted by one device received as it is at the receiver or not, for that testing of parity of the data is technique is used. Where meaning of parity is what? In case of group of binary bits 1 and 0, strings of 0 and 1, if the number of ones, that means bit 1, present in data, that decides the parity of data. That means binary data can include zeros as well as ones, number of ones, number of zeros. But number of ones are used to identify the parity of given data. There are two types of parities, depend upon number of ones. First is the odd parity. In case of odd parity, if the given binary data contains number of ones present in it are odd, then the parity of data is to be said odd parity. For example, suppose there are 3-bit data is there. In the first combination, all 3 bit as 1 1. So 1, 2, 3, number of ones are 3. 1 appear 3 times. So odd. In second example, 1 0 0, 3-bit data, here 1 appear only once. So again single time means it is an odd number, so parity is odd. Here in the example we have the example of 5-bit data in which binary bits are 1 0 1 0 1. So number of ones are 1 2 and 3. So odd number parity purchased by the 5-bit group of data is odd. One more example, again an example of 5-bit data in which binary bits are 1 0 0 1 1. Here also number of ones are 3, therefore it contains an odd parity. One more type of parity is even parity. Meaning of even parity, if the data contains number of ones present in it are even, that means number of ones in the string of 1 and 0 are even numbers, then data is said to be of even parity. For example, suppose we have again example of 3-bit and 5-bit. So first one here, 3-bit data contain the binary bits as 1 1 0. So here number of ones are 1 and 2, means 2 times 1 appear, so parity is even. Second example also you can see here 1 0 1. Here also 1 appears twice, so parity is even. In case of 5-bit of data, binary bits are of 1 0, 3 times 1. If you count number of ones 1 2 3 4, so parity is even. As well as in the last combination, if you observe number of ones are here 1 1 1 1, means 4 times, again an even number, so parity is even. So again the question left here, why do we go for the testing or checking of the parity of data? Before data to be sent, its parity is tested or checked by a logic circuit. We'll see about it very soon. As well as the same data is received by another device. So at reception, also once again parity is checked. If the parity of data possessed before to send in transmitter, same parity is observed in the data received at receiver. That means number of ones or string of 1 and 0 it remains same by having same parity. Therefore, we can check if any error present in the data transmission. A simple method for testing of error, that is parity testing or parity checking. Let's see here now how we can test the parity by using XOR gate. For example, here 3-bit parity checker by using logic gate exclusive OR or XOR. Very simple circuit. Very first, a circuit diagram of 3-bit parity checker that is known to us. To check the parity of 3-bit data, we can use 2 XOR gate in this way. 2 input to XOR gate because we want 3-bit. So first XOR gate having input A, B, its output along with third input C given to the one more XOR gate. So we can implement 3-bit input by using 2 input XOR gates. This circuit will work as 3-bit parity checker. Will check the parity of data. Or you may have A single XOR gate having 3 inputs as ABC also available. So here again the Y as an output. This output Y will tells what kind of parity possess in the 3 bit of input number. Output will tells the kind of parity or type of parity possessed by the data present at input. And for this, for sake of understanding, let's we have the working with the help of truth table of parity checker. As we have discussed, by using logic gate XOR, we can write a by using 2 input XOR gate, we can write a truth table for 3 input XOR gate. Let's see a truth table for 3 input XOR logic gate. By reminding truth table for 2 input, you can extend it for the three number of inputs. See here, A, B, C are input and Y is the resultant output for 3 input XOR gate. Just think about first 2 bits. We know that 0 XOR 0 in a 2 input XOR gate, output is 0. Again that 0 XOR with third input 0, again output comes to be 0. For second combination here, 0, 0, 1, 1. So first XOR gate, 0 XOR 0, result can be 0. But its output XOR with 1, result can be as a 1. Similarly, here 0 XOR 1, it is 1. 1 XOR 0, again result as a 1. Here 0 XOR 1 by the first 2 input XOR gate, result can be as a 1. This 1 again XOR with 1 by truth table of 2 input XOR gate. 1 XOR 1 will comes 0. Here 1 XOR 0 will be as a 1. Again 1 XOR 0 will get as a 1. Here 1 XOR 0, 1. But 1 XOR 1 will come 0. 1 XOR 1 will be 0. 0 XOR 0 again comes 0. Here again in the last combination, 1 XOR 1 will be 0. But 0 XOR 1 will comes 1. Or just remember, very simple technique behind the resultant output for the input ABC. Wherever you find number of ones in odd figure, see here 1 appear only once in this 3-bit, 1 appear only once in this 3-bit, 1 appear here twice. That means odd. But 1 appear here only once. Sorry, 1 appears here twice means even. 1 appear only once. Here it is a twice. Here it is again twice. Here 3 times. So wherever you find binary bit 1 appears in odd numbers 1, 1, 1 times and 3 times, there we have the output as 1, 1. So your output becomes 1, output becomes high when the number of ones present in the input are odd. That means what we find, it is found that the output of 3-input XOR gate becomes high when it has odd number of ones at its input. That means high output represent or indicates that the data possess odd parity. Is that clear? A very simple technique. We can extend this concept for the 4 inputs. Say example here, working of 4-bit parity checker, where you can use 3 number of 2-input XOR gate, or you may have single 4-input XOR gate also. Let's see about only its truth table. Truth table for 4-bit input XOR gate. These are the 4 inputs A, B, C, D, and this one is the output as a Y. Output is Y over here, sorry. So here, if you observe in 4-bit data, wherever you find number of ones are in odd, means 1 times, 3 times, then only output becomes 1. With the all possible combinations of 4-bit inputs beginning with all 4 at 0, 0, it will end all 4 becomes as 1, 1, 1. Wherever you find number of ones odd in figure, here single time 1 appear, so output goes 1. Here also in 4-bit, single time 1 appear, output goes 1. Here also binary bit 1 appear only once, so output is high. Here it is again 3 times 0, 1, 1, 1, 3 times 1, so output goes high. Here single times 1, so output high. Here again 3 times 1, output goes high. Here 3 times 1, output goes high. Here in case of 1, 1, 1, 0, 3 times bit 1 appear, so number of ones are odd, therefore output high. Here also the high output for the 4-input data represent the parity purchase is the odd, otherwise output is 0. Remember that parity decided by whom only? Parity decides by only number of ones present. If it is in odd, output of XOR gate will goes high. So in this way, we found here that the output becomes high if number of ones present in the 4 bit of input data is odd. Therefore, the testing of parity is made by using XOR gate. Its output will represent the parity purchased by the data. In case of 4-bit, we can use 4 input XOR gate. Output high indicate that the input data has an odd parity. Is that clear? Now we'll go for second application of XOR gate, that is control inversion or control inverter by using an XOR gate. Very simple concept. We can understand the concept of control inversion with the help of 2 input XOR gate. Let's here we are having 2 input XOR gate. With the first case, inputs can be as A and B. Out of 2 input, second input is at a ground connection. In case of positive logic, we can take ground means logic 0. So B taken to be as here 0. A can be either X, either 0 or 1. Let us find what will be the resultant output for this 2 input XOR gate with one of the input B taken as a controlled input which is held at logic 0. Equation for 2 input XOR gate is what? A and B bar or A bar and B. Now put the value of B as here 0. Equation becomes as A and 0 bar or A bar and 0. Now as you know, complement of 0 becomes as a 1. Ending of any number with 0 will remain as a 0. So A and 1 will remain as a only. A or 0 will get final result as a Y equals to A. Thus, if out of 2 input, 1 input B taken as a control input, if it is at logic 0, output will be same that of remaining input without any change. If A is 0, output comes 0. If A is 1, output will comes again as a 1. If second input is at logic 0. Exactly opposite. You can take second case here when B is equals to 1. As a second, one more case here in which out of 2 input, B input is at plus VCC. In case of positive logic, plus VCC means logic 1 or high level. So B is equals to 1. Let's see again now here verification by using equation for 2 input XOR gate Y equals to A and B bar or A bar and B. Now put the value of B as here 1. It becomes equals to as A and 1 bar or A bar and 1. Now inversion of 1 bar becomes as a 0. That means A and 0. Here only A bar and 1 means only A bar left. But ending 0 with A will get cancelled as a 0. So what left only? A bar as a final output. So Y will be equals to A bar as a resultant simplification for equation for the output when one of the input is at logic 1 taken as a control input. Thus, what we found, when the control input taken here B is at logic 0, output will be same, that is Y equals to A, that of remaining input. But when control input is at logic 1, then output will be inversion of the remaining input. That means if B is at 1, Y equals to A bar as an inverted output. Thus, out of 2 input, 1 input can be taken as a control terminal by which we can control the operation of XOR gate as a NOT gate or inverter. Therefore, it is called as controlled inverter use or application of an XOR gate. We can extend this for the practical application as a circuit of 4-bit controlled inverter, where you'll find we want to make a 4-bit of data same as it is at the output or with 1's complement, means inversion of all bit 0 into 1 and 1 into 0, that we can obtain by using a simple construction by use of 4 2-input XOR gates. We can use the 4 number of XOR gate with each of them having 2 number of inputs like shown in this figure. So we are having the 4 XOR gate here. 0th position, first position, second and third. Suffix 0 for LSB and suffix 3 for the MS bit for 4 bit. In which, in the construction what we have seen, 4 bits data A3, A2, A1, A0 applied as a one input for each of XOR gate. Then remaining input from each XOR gate is coupled together to a common input that is called as invert input. Then resultant output we find here again of 4 bit by all these 4 XOR gate in a sequence as Y3, Y2, Y1, Y0. These output will be either same that of input A3, A2, A1, A0 or will be inverted of A3, that means A3 bar, A2 bar, A1 bar, A0 bar, depends upon this control common input that is called as invert to all these 4 XOR gate, where you'll find that when invert is equals to 0, as we have discussed, if one of the input for XOR gate taken as a control input is at logic 0, it is here now invert. Each XOR gate will pass remaining input to its output. Y0 equals to A0, Y1 will be equals to A1, Y2 will be equals to as A2 and Y3 will be equals to as A3. That means resultant 4-bit output Y3, Y2, Y1, Y0 will be same that of inputs A3, A2, A1, A0 when invert is at logic 0. On the other hand, when the common input invert is at logic 1. In that case, as per our previous slide discussion, you have seen that if one of the input taken as a control it as logic 1, then the output of XOR gate will be inversion of remaining input. That means if this one input is high, output Y0 becomes as A0 bar, Y1 also becomes as A1 bar, Y2 becomes as A2 bar, Y3 becomes as a A3 bar. That means resultant output can be as inversion of all the inputs. That means Y3, Y2, Y1, Y0 will be equals to A3 bar, A2 bar, A1 bar, A0 bar. That is called as one's complement. Idea will be more clear as a part of working with the help of truth table of 4-bit control inverter. See here, very simple constructions. We have the one input as a common called as invert input. 4-bit data input can be as A3, A2, A1, A0. We can have the any combinations. Possible number are 16. Just I have taken only couple of for sake of understanding. Now resultant 4-bit output of logic diagram that we have learned will be of Y3, Y2, Y1, Y0 as a 4-bit data output for 4-bit control inverter. Now see here, when the invert is at a 0, when the invert is at a 0 and let the 4 inputs are also at 0, 0, 0, 0. In that case, the 4 output remains same that of 4 input 0, 0, 0, 0, 0. That means no any change. Output will be released at, input will get released at output as it is without any change if invert common input is at logic 0. But when keeping the same input 0, 0, 0, 0, now if this time invert input is at logic 1, then as a result every bit will get inverted. Resultant output can be as 1, 1, 1, 1 for input all 4 zeros because of inversion. You can take one more example. Second example is of data 1, 0, 1, 0 is applied as input A3, A2, A1, A0. Now first case, if invert is 0, same data produce at the output without inversion. But if invert is made at logic 1, data remains 1, 0, 1, 0, output get inverted 1 into 0 and 0 into 1. Therefore, resultant 4-bit output can be as 0, 1, 0, 1. So what we find here, when invert is 0, then the output will be same that of input. When invert is at logic 1, then the output is inversion of the input. So with this, we can get 4-bit output as the ones complement of applied 4-bit input when invert is at logic 1. This technique we will learn in our next session is used in the common hardware that either it can add 4 binary bit, in that case no inversion of second number, or it can subtract 2 numbers each of 4 bit. In that case second 4 bit can be inverted by using 4 XOR gate as a controlled inverter to get the subtraction between two numbers. Idea will be more clear once we go for the next content in our next session. So in the next presentation, we shall go for study of laws of Boolean algebra and its implementation, where you'll find how we can represent logical operation in terms of Boolean equation, then how we can simplify it by using various laws of Boolean algebra. After then, with the simplification, you'll try to understand big size of logic diagram will get reduced into the very small size as its advantage of Boolean algebra. That will be more clear in our